This is St. Louis on the Air from St. Louis Public Radio. I'm Elaine Cha. To start our next conversation, here's a clip of a scene from Mike Nichols' 1967 film, The Graduate.
I just want to say one word to you. Just one word.
Yes, sir.
Are you listening?
Yes, I am.
Plastics.
Exactly. How do you mean?
There's a great future in plastics. Think about it.
Those lines became classic from Mike Nichols' 1967 film, The Graduate, for their mockery of the superficial, the unoriginal, the easy. But wherever you are at this very moment, take a look around. How much of what you see is made of natural materials, and how much of it is not? As it turns out, that one word, plastics, did indeed have a great future. A future so good, it's bad, and it's now all over the planet, causing serious environmental harm and bringing along other detriments. To mitigate that damage and offer alternatives to plastic everywhere, a team of researchers at Washington University is working to develop a new variety of materials, ones that are environmentally sustainable and inspired by nature too. Here to discuss that, we have Marcus Foston, Associate Professor in the Department of Energy, Environmental, and Chemical Engineering at Washington University in St. Louis. He's leading a multidisciplinary research team studying how to combat plastic waste. Marcus, welcome.
Thank you. I'm glad to be here.
We also have Fuzhong Zhong, who is a professor in the same department at WashU and part of that research team. Marcus and Fuzhong, welcome, and thank you for joining us today.
Thanks for having us.
Now, Marcus, most people understand that plastic pollution is a huge environmental problem. And I'd venture to say that the first thing many folks think about is harm to marine life. But what does plastic pollution encompass? And, what are its impacts on the planet?
Yes. So as you mentioned, plastics are ubiquitous in our modern economy. Something like 30% of plastic packaging escapes common collection systems. So even when we're really trying to recycle and be environmentally friendly, our typical waste processing leaks these plastics into our environment, and we find them in our soils, we find them in the water, and often turn into these really small nanoparticles that can get into like everything.
Mm-hmm. And on that note of recycling, how much of this plastic is produced by us humans, and then how much of it actually gets recycled?
Yes, so often there's not a real big economic incentive for recycling. After you recycle a plastic material a few times, there's this kind of thermal processing, heating that has to happen. Usually there's degradation in the properties of that material due to the heating and the contamination. Mm-hmm. And so often, even in some of the streams that we dedicate towards recycling, those streams actually get sold to people that then put them into, let's say, landfills.
Mm-hmm. Now, you mentioned the costs involved, and plastic waste has natural environmental harms, but there are serious economic problems that come along with that too. So a lot of money and value is lost. How does that happen? Can you expand on that a little more?
Yes. So we're producing plastics from petroleum, and that process of generating the monomers that go, or the building blocks that go into those plastics, is actually a quite valuable. Produces something that's quite valuable, and so as this material leaks into the environment, we see losses just to the loss of that on those materials, something on the order of about $80 to $120 million a year annually can be associated with the loss of these plastics into the environment.
Mm-hmm. So when you say leak, it's not like a dripping, it's like stuff falling off trucks? What does leak constitute?
Well, in theory, we would want to be able to say if we're able to put plastics and have them go into a landfill and we actually bury that, in theory, it should be captured fairly well in that landfill and we wouldn't be having a lot of the environmental issues that we're talking about. And so between us, putting the plastic in the trash can and then it eventually making it to the landfill, there's places where that material in some way falls out of that intended delivery.
Mm-hmm. Now, plastic waste is all around us. And it's talked about so much as a global issue that sometimes I think maybe it feels far away or abstract even. Now, on the local level, how is plastic waste affecting St. Louis and nearby communities?
Right. I mean, we think about the ocean a lot, and there's a lot of stats that suggest that there's going to be more plastic in the ocean than fish by the year 2030 or so. Mm-hmm. Not 2020, it's 2030. And so, but then if we think about locally, there's a lot of environments that are aquatic based. So we're thinking about the Missouri and Mississippi rivers, mm-hmm. The Great Lakes, and so we see a lot of plastic pollution that can happen in those environments. And there's even plastic pollution that we've been able to determine are in urban areas as well, in the soil, and these things make it eventually into the wildlife and then eventually into human bodies as well.
Mm-hmm. Now, let's talk about the research. So, Fujun, you've been involved with this, and the central question that you and others on your research team are trying to answer is how can we produce natural materials to replace plastics? Can you explain the scope of your research?
Yes, sure. If you think about what human being has been getting materials, a century ago, before human invented plastics, we are getting materials mostly from nature, or getting materials from wood, from different agricultural products, and from other natural resources. Many of those materials are degradable, so that once we use them, they do not produce harm to the environment. Mm-hmm. And then once we start to use the plastic, we have all these problems. Now the idea is whether we can go back to search for a new natural solution for plastics, whether we can produce these materials by nature and through a more environmental friendly way. And once we use the material, they also will be able to go back to nature, have the material degraded without causing problems in oceans, in water system, and in soil.
Mm-hmm. Now, a lot of the materials that you are working on producing, they take cues directly from the natural world, as you've been talking about, and organisms in particular. What is an example of that?
Right, exactly. So the microorganisms is the catalyst, if you will, that we engineered to help us produce these materials. Alternatively, we can get material from plant, but however, plant have a grows really slowly. And to support the current modern society's need, we would like to have a much faster way to produce these materials. That's how we use microbes. I can give you examples. Right now, people are already using microbes to produce other type of products, such as antibiotics. And the microbes, some of them has been engineered to work so well to produce enough amount of antibiotics for the whole world. But there really hasn't been too much technology developed to make materials, which will be the next huge challenge that what we working in the center is trying to address.
Yes. And from what I understand, there is a synthetic fiber that you've produced.
Yes,
Talk
exactly.
about that. Yeah.
Sure. So the research in our research lab started from some natural materials that we know of. One of the best example is spider silk fibers. Spider silk fibers has a outstanding mechanical properties that people has trained to replicate using other ways, but it's turned out to be so challenging to make spider silks from other ways. And also, you cannot really farm spiders because they start to eat each other when they grow too closely. So definitely that's not the route. And other groups has been trained to produce spider silk from different species, but then all facing problems.
Yeah.
We have been trying to solve this problem using a new field of research we call it synthetic biology, where we genetically manipulate the microorganisms, allow the organism to learn all the tricks that nature has involved so that this bacteria can produce spider silk materials and have their properties very similar to the natural spider silk. So now we create these fibers in the lab scale and demonstrate that they have all these amazing mechanical properties that can be used for a wide variety of different applications.
Mm-hmm. That sounds like the premise for another Spider-Man movie. Now, insofar as the research team and application goes, Fuzhang, you and Marcus have been collaborating on research for several years now, but thanks to a $3.6 million National Science Foundation grant, which you have just received, it was in May, some things have changed. So your WashU team now has partnerships with other universities like Northwestern University, as well as with people with expertise in machine learning. Fuzhang, how do you foresee this variety of partners affecting the work that you've already started?
Right. So working in a highly collaborative environment is really helpful for us. My group has usually been focused on developing synthetic biology technologies to trying to solve the scientific problem. But of course, there's many other things we need to consider. There's a social impact. Once we have this technology, what type of material we should really use it to make. Whether that will be able to bring the biggest social impact. So we have the social scientists working together with us. We also have people with strong material background that can tell us what type of material properties will be better needed and for us to design. And also, as you mentioned, we have people with expertise in machine learning, in modeling, who can much better help us design and create the best material. Mm-hmm. So working in such a collaborative environment would much efficiently improve our productivity and allow us to do many new things that just by a single group we cannot.
Right, right. Now, Marcus, your research team includes supply chain experts and economists. We mentioned it's multidisciplinary, right? And one of your long-term goals is to get manufacturers and consumers to adopt these new non-plastic alternatives. Tell us about why involving these kinds of experts is important in these early stages of research.
Yes, so I teach a course on these kinds of questions, and one of the stories I like to tell is the story about the sun chip bag. So they were making sun chips, and they wanted to have a bag that was a little bit more environmentally friendly, and they made it out of a plastic that was renewable, mm-hmm. And they engineered it. They engineered it so it kept the chips from going bad. They could print on it really well, but then the consumer rejected that product. And they found out it was because it crinkled too much.
Oh, it was too noisy?
It was too noisy.
Okay.
Right? And so often trying to understand the drivers and the barriers for technology adoption, even at an early stage of engineering and of understanding a material, can be very, very useful in that technology development. And so that's what we're trying to do here.
Okay. That's a very vivid example. Thank you for bringing it to the everyday level. The materials that your team is producing, it has great potential for use in things like packaging, the chip bag, in construction. But one way you hope to apply the materials is in biomedicine. So give us an example, Marcus, of how a product that you can produce could work in a hospital, for instance.
Yes. So these materials, not only are they biodegradable, but because they're of natural origin, they often have biocompatibility properties. And again, we're really interested in engineering the mechanics of these materials as well. And so one example is that we're working with some people from the medical school at University of Washington University to generate a new hernia mesh. right? And so these are just implants that you might put into the body if you have a certain type of injury. And then because it's biocompatible, because we can tune the mechanical properties in a specific way, and we can 3D print these materials, maybe we can make these new types of implants. And the ability to be able to tune properties using these using DNA to design the material, and using genetic engineering is something that gives us an advantage, to say, to other types of materials that are out there.
Now, in this final question here, both you, Marcus, and Fuzhang, you are not from St. Louis, but you've been here for some time. Fuzhang, you're originally from China, and Marcus, you're born and bred in Georgia, right? Tell us about how you two have engaged with students and business in St. Louis and why that is a priority.
Yes. So one of our major missions is education, and that's part of the reason why I do the job. But also we are looking towards workforce development in a future where we are using biomanufacturing and genetic engineered microbial systems to produce materials. There's going to be a new set of job demands, and we want to make sure that we are thinking about what those are and how to meet those, particularly at a local level in St. Louis. The educational component, we're really interested in impacting K through 12. And so we really want to go out in our surrounding schools and really be able to deploy some of the technologies that we're doing to excite young kids.
In about 20 seconds, Fuzhang, how about you?
Sure, yeah. I also want to add that we believe St. Louis is a very unique area. Particularly, we are very closely with industry, and St. Louis is a very unique area that the entrepreneurship in biotechnology and agriculture is very active. So we're really looking forward to work with local industry on our products.
Great. Fuzhang Zhang is a professor, that is, in the Department of Energy, Environmental, and Chemical Engineering at Washington University in St. Louis, and he's working on the team led by Marcus Faustin, who is an associate professor in the same department, Energy, Environmental, and Chemical Engineering at Washington University. And we wish you luck in your endeavors.
Thank you.
Thank you.
Today's segment was produced by Aula Kuzitz. Audio engineering and podcast design by Aaron Dorr.
Our executive producer is Alex Hoyer.
St. Louis on the Air is a production of St. Louis Public Radio. Understanding starts here.
St. Louis on the Air proudly supports local artists by using music from Life Creative Group.
Do you find yourself regularly listening to episodes of St. Louis on the Air? Suggest us to a friend you think might enjoy our conversations, and leave us a review and rating on Apple Podcasts on the App Store. It's the simplest way to help people discover our show. Thank you.
St. Louis Public Radio is a member-supported service of the University of Missouri St. Louis.
Support comes from the Missouri Forest Products Association, committed to conservation and careful management of the state's forests to make them more resilient and better habitats for wildlife. ChooseWood.com.